Hello everyone, I'm Smita Swain, a graduate student at the Material Science and Engineering program at Arizona State University. Today I'm making this video on the topic of spinodal decomposition in binary alloys as a part of my coursework for the MSc 598 Microstructure Modeling and Simulation classes. Today we're going to learn about what a spinodal decomposition process is and how it differs from the nucleation and growth process. We will also look at the phase field modeling aspect for this process and also develop an algorithm to program phase field modeling of spinodal decomposition process in C program. We will at the end simulate and observe the spinodal decomposition process. Spinodal decomposition is a mechanism through which a single phase splits up into two phases. These two phases vary with respect to each other in terms of chemical composition and physical properties while they have the same crystal structure. Now let's look at the differences between spinodal decomposition and nucleation and growth process. The phase separation due to spinodal decomposition is much more defined and occurs uniformly throughout the material, not just at discrete nucleation sites, which is the case for nucleation and growth process. There is no thermodynamic barrier to the reaction inside the spinodal region. The decomposition is determined solely by diffusion process. Thus, the process can be treated purely as a diffusion problem, and many of the characteristics of the decomposition can be described by an approximate analytical solution to the general diffusion equation. In contrast, the theories of nucleation and growth have to invoke the thermodynamics of fluctuations, and the diffusion problem involved in the growth of nucleation and growth is far more difficult to solve because it is unrealistic to linearize the diffusion equation. Spinodal decomposition involves an uphill diffusion or a negative diffusion coefficient, whereas diffusion is always down a concentration gradient for nucleation and growth process. Let's look at this picture to get that picture a little more clear. Over here you can look at the spinodal decomposition process where we have two types of movement. One is up the hill and one is down the hill. That is where you find two different phases. Whereas nucleation and growth, there is only a downhill motion as the atoms from the surrounding environment come together to the nucleation site, and as a result the nucleation site grows. As a special case of phase transformation, spinodal decomposition can be illustrated on a phase diagram exhibiting a miscibility gap. This phase separation occurs whenever a material transitions into the unstable region of the phase diagram. The boundary of the unstable region, sometimes referred to as the binodal or the coexistence curve, is found by performing a common tangent construction of the free energy diagram. Inside the binodal is a region called the spinodal, which is found by determining where the curvature of the free energy curve is negative. The binodal and spinodal meet at the critical point. It is when a material is moved into the spinodal region of the phase diagram that the spinodal decomposition can occur. Now look at the phase diagram and free energy diagram of a spinodal decomposition process. If an alloy with composition of X0 is solution treated at high temperature T1 and then quenched to a lower temperature T2, the composition will initially be same everywhere and its free energy will be G0 on the free energy curve. However, the alloy will be immediately unstable because small fluctuations in the composition that produces A-rich and B-rich regions will cause the total free energy to decrease. Therefore, the uphill diffusion takes place until the equilibrium compositions of X1 and X2 are reached. In comparison, if an alloy outside the spinodal, that is depicted here with the composition of X0 prime, is solution treated at a high temperature T1 and then quenched to a lower temperature T2, small variations in decomposition lead to an increase in free energy and the alloy is therefore metastable. The free energy of the system can only be decreased in this case if nuclei are formed with a composition very different from the matrix. Therefore, outside the spinodal decomposition, the nucleation growth process takes place and transformation of alpha to another phase, single phase, happens. Equilibrium phase composition are those corresponding to the free energy minima in this diagram over here. The regions of negative curvature that is identified where the slope, that is dou squared g by dou c square, is less than 0, lie within the inflection points of the curve, that is again can be found out where dou squared g by dou c square equal to 0, are called the spinodal points, which are marked as S1 and S2 in the diagram above. For compositions within the spinodal, a homogeneous solution is unstable against microscopic fluctuation in density and composition. There is no thermodynamic barrier to the growth of a new phase, that is, phase transformation is solely diffusion controlled here. To reach the spinodal region of the phase diagram, a transition must take the material through the binodal region or the critical point. Often phase separation will occur via nucleation during this transition, and spinodal decomposition will not be observed. To observe spinodal decomposition, a very fast transition, also called a quench, is required to move from the stable to the spinodally unstable region of the phase diagram. Now let's look at the phase field modeling aspect of spinodal decomposition. Imagine the growth of a precipitate which is isolated from the matrix by an interface. There are three distinct quantities to consider: the precipitate, the matrix, and the interface. The interface can be considered as an evolving surface whose motion is controlled according to the boundaries condition consistent with the mechanism of transformation. The interface in this mathematical description is simply a two-dimensional surface with no width or structure. It is called to be a sharp interface. In the phase field method, the state of the entire microstructure is represented continuously by a single variable known as the order parameter phi. For example, phi equal to 1 represents the precipitate, phi equal to 0 represents the matrix, phi when it varies in between 0 to 1 represents the interface. Therefore, the interface is located by the region over which phi changes from its precipitate value to its matrix value. The range over which it changes is the width of the interface. The set of the values of the order parameter over the whole microstructure is the phase field. The evolution of the microstructure with time is assumed to be proportional to the variation of free energy functional with respect to the order parameter, which is given by dou phi by dou t is equal to m into dou g by dou phi, where m is the mobility. The term g describes how the free energy varies as a function of the order parameter at constant temperature and pressure. This takes the form of the following equation, where v and t represent the volume and temperature respectively. The second term in this equation depends only on the gradient of phi and hence is non-zero only in the interfacial region. It is a description therefore of interfacial energy. The first term is the sum of the free energies of the precipitate and the matrix and may also contain a term describing the activation barrier across the interface. For the case of solidification, G naught is given by h into G solid plus 1 minus h into G liquid plus Q into F, where G solid and G liquid refer to the free energies of the solid and liquid phases respectively, and Q is the height of the activation barrier at the interface. We can see that h and phi is given by the following functions. Notice that the term hg solid plus qf vanishes when phi equal to 0, that is, it is only liquid. Similarly, 1 minus h into g liquid plus qf vanishes when phi equal to 1, that is only solid. As expected, it is only when both solid and liquid are present that qf becomes non-zero. The time dependence of the phase field then becomes and is given by the following equation. The parameters q, epsilon and m have to be derived assuming some mechanism of transformation. Two examples of phase field modeling are as follows. The first is where the order parameter is conserved and is given by Cahn-Hilliard transformation. With the evolution of composition fluctuation in the precipitate, it is average chemical composition which is conserved. On the other hand, the order parameter is not conserved during grain growth, since the amount of grain surface per unit volume decreases with grain coarsening, and this process is known as Allen-Cahn equation. We should further simplify all these equations, and on further simplification we get f of phi reduced to this equation. Now we take this equation and the rest of the equation and substitute in the differential diffusion equation to get the following equation, which is very famously known as the Cahn-Hilliard equation. Let's look at the algorithm for programming this in C. Create variables for the required program, that is material characteristic properties, time spacing, grid spacing, etc. Once you're done creating the variables, you need to initialize and assign them in some default values. You can use pointers in this process, but one needs to take care of allocating memory and deallocating memory when working with pointers. Now you need to have a function that would create a local variation or fluctuation in the phase field phi value by varying the composition or concentration parameter. You then need to create another function that has to solve the phase field differential diffusion equation, also known as the Cahn-Hilliard equation, using finite differential method. Now, after this, you need to have another function that would set the boundary conditions and also create appropriate functions to save the data in required form for plotting the results finally. Now I'm going to run the program in C using Genie in Ubuntu. That was the evolution of spinodal microstructure. Thank you for watching.